Okay, now let's talk about the learning objective of this course. So this course, design a controller for your work or for your maybe research. So I eventually I hope that you model the dynamic of the system and analyze the system and control the system. So the dynamics of the system means that electrical system similar to fluid or mechanical system or electromechanical system such as motors and gears. This can be a part of the robot or a car. And analysis the system means that you understand the speed of the response or the error between the your desired speed or actual speed. So Trojan response typically means that if there's this, let's say this is time, and this is velocity, it can be car velocity. So let's say your desired velocity is 70 miles per hour. And when you accelerate your car, sometimes your car responds very slowly, or sometimes your car responds very fast. So this is called the transient response, and then steady state means that whether it can reach 70 miles per hour or maybe 75 miles per hour, even though your desired speed was 70 miles per hour. So that's the analysis the system, and control the system means that using linear control technique for this course, such as PI or PID controller, you can actually change the response. So let's say originally your system response is similar to 1. You can change the system response to very fancy. Maybe even something like this. It's very fast, also reach steady state, reach exactly the velocity, the same velocity you want within a very small time. And to do so, you will learn some tools such as complex number, which actually it's a review of the tools, complex number and Laplace transform. And then we learn the root locus and body plot. So you already know, I think, dynamic systems and then control. So let's review what is the dynamic systems. You already learned the dynamics, or fluid dynamics, or thermodynamics, or gas dynamics. So let's review it, and then what is the control means, and what does the controller design process look like. So this is an example of the dynamic system which I controlled in a workplace such as Samsung, and which I controlled the motor using a motion planning technique, using dynamic simulation tool. And so believe or not, this is not, I didn't do this, but the toilet actually can be a perfect mechanical dynamic system and control example. So let's see how the toilet looks like. So this is developed by Joseph and Thomas. So this is how the system looks like.
Low shift the toilet valve usually has a ring shape.
Oops, there's some echo, so I just stopped. So I explained where even though my pronunciation is not that great, you can come to this and then do it. So this is a mechanical valve, which is a sensor. So this valve is a sensor, and depending on the sensor, the reading, the water can be filled. So this entire system is a kind of a controller using a mechanical design. So, oh, where's my PowerPoint? So this, so please go to the link and you can review the mechanical system, or actually we go for this example. So what's the dynamic system? Any idea? So dynamic system is the system that evolves with time. What does it mean? Typically, these systems have inputs and outputs. And we want to understand how the input affects the output. Typically, these systems is modeled by ordinary differential equations, ODE, which satisfies linearity and time. So we can design a linear controller about the fixed point or operation point. And by doing control, we want to design a system that ensures desirable properties. So for this toilet system, we want to make sure the water is filled almost all the time after we flush this toilet. That's the controller. So in a dynamic system, the system is dynamic if its input depends on the past. So the alternative concept is a static system if the output only depends on current input to system. So let's look at the example. These are the current static system because the output depends only on the current input. Can you come up with any example of the static system? So something like spring, which is y equals kx. That is a static system because the output, the force, or F equals k delta x, depends only on the current input. Dynamic system depends on post inputs or outputs. So typically dynamic system has dy over dt, which is depends on the time story. So these are the another definition of a dynamic system. And the controller, by designing a controller, we want to make the dynamic system behave something what you want to like. So there's a called a feedback control system, which is a control system that tends to maintain prescribed relationship of one system variable to another by comparing functions of these variables. So that's what this controller do, using them as a means of control. So the feedback control system looking at the plant output and compare this output using a sensor and then provide a control input to an actuator which drives the plant. So therefore the plant can do a desired behavior. That's feedback control system. So it is called feedback control system because you are getting the output signal to a controller, so it's called the feedback. Or it's also called closed loop system. But there's another concept, which is open loop system, which doesn't have this part error. So doesn't look at the control output error. So that's open loop system. But this is a feedback control system, which look at the input output variable and drive the actuator. So therefore the plant can do a desired, can show desired output, such as a speed control, where your desired output is 17 mile per hour. Well, desired reference is 70 mile per hour, and then leading your output, which may be 60 mile per hour. Then compare this reference to the output. And because it is slower, the controller commands the actuator, please provide more power. So then actuator provides more power to the plant. So therefore, the plant, which is your car, can achieve 70 miles per hour. So we come back this again. But also I given another example of Ankle-foot prosthesis. So ankle-foot prosthesis is this one part, which is here. And it has actually actuator and controller and end effector with a person, which can be this entire part can be a plant. And the sensor can measure torque or position, and depending on the reference, the controller decides control input to the actuator, and the actuator drives the plant. So this is a sensor example. So actually we made also sensor. So the sensor measures torque. So you can see over here. So when he adds more mass, this reading gets higher. And the sensor, actually, so we made a sensor using this no mass. And so therefore, this ankle-foot prosthesis can measure torque depending on the control input or depending on the situation. So there's a sensor which can measure the plant torque, and in this case, and using this sensor, we can do called step response test. So if you can very carefully see, these two pushes this bar. Let's see, can you see? This two pushes this bar, which is shown here. So like the blue is desired torque and orange is actual torque. And actual torque tries to reach to the desired torque. And how can you do this? So this entire thing is a plant. And then there's an actuator, which you saw before, and controller commands control input to the actuator by comparing reference and an output. So in this case, reference is blue and is orange torque. In the previous slide. So for this controller design, we need to decide what is our objective and what is the design requirement and what kind of tools we have. And then we can design a controller. So for the previous design, the objective was to meet the desired torque as soon as possible. So here, it's a little bit slow, but actually we hope that it can reach desired torque really fast without any delay. But we have the constraints such as maximum current and the maximum velocity. So that was our best. And for the modeling, so in the beginning, we modeled the system using Laplace transform and then transfer function, and then did system analysis, such as steady state error or transient response. And we used MATLAB that was called MATLAB Simulink and designed a controller. And towards the end of class, you will learn this process. So this is one example of like after you are doing all this process, this is what you see. You will see the time response of the system. And this is called frequency response using body plot. So this is another response in the inversion eversion. And this is the actual frequency response, which I show later again, but this is actually a combination of the sine wave. And you can see something like this frequency response curve. And after all doing this, you can design a controller which can follow your desired torque trajectory really well, almost perfectly. And then maybe you can win another best paper award. So this is our feedback control system, which we learned through entire semester. And in the beginning, we learn how to model the system such as plant or actuator or sensor. So that will be called modeling the system. And then we will use our Laplace transform. Then we learn how to analyze the system, such as something like this. This is actually system analysis result. So this says the falling time is 24 milliseconds and rise time is 33 milliseconds. So I write down. So you will later you will look at rise time and falling time. Actually, it's another rise time, and also system bandwidth. So this is actually system analysis. And you will design a controller to minimize this rise time. So you want to design a controller something like this to behave something like this step response. So this will be your entire process of the feedback control system design, and then controller. It will be linear controller, such as PID controller. So you learn modeling the system and then look at output. So look at the transient response. And steady state response. I like better. So this is system response. So you will first learn how to model such actuator and then plant and even sensor. So, and you will learn how to analyze transient response and the steady state response by comparing between reference and output. Then the final step is designing a controller to make response faster with minimal error. So this is it. And I'm looking forward to seeing you tomorrow morning. Bye.